Hi, my name is Raja. I work as a part of the Coherence engineering team, and today I'm going to speak to you about a new feature we've added in Coherence 12.1.2 called the POF Configuration Generator. So we'll start with a bit of an introduction around POF, talk about how objects conform to the POF contract today, and then we'll talk about some of the problems that we believe are present and we hope that the POF Configuration Generator resolves. So currently, to conform to the POF contract, you either implement portable object or you provide an auxiliary object which implements a POF serializer interface. The benefit of the latter approach is that your object remains unpolluted of serialization logic, and as well as that, it doesn't have a dependency on the serialization framework that's being used. In Coherence 3.7.1, we introduced a couple of annotations, namely portable and portable property. The intention of these annotations was to ease the developer experience in using POF. So, opposed to having to implement an interface, you would simply mark the things that you wanted serialized as either portable for the classes and portable property for either the fields or the methods. So let's have a quick example and take a look at what it looks like to conform to these contracts and the various mechanisms we just outlaid. So first of all, we have this atom class, which has a number of electrons and also has a nucleus. And as you would imagine, the nucleus has a number of protons and neutrons. So let's have a look at the portable object interface. So here, atom implements portable object. We implement the read external, we implement write external methods with the appropriate serialization logic. At the bottom here, we can see that we have an XML snippet. The XML snippet is used by a POF context. So the configurable POF context, it can be configured via XML. And so this XML registers a user type ID of 1000 with a class name of atom. And as you can see, there's no element under the user type which is called serializer. And this is because from the atom class we can infer the serializer to be used based on the fact that it implements portable object. The POF context requires this XML because the responsibility of the POF context is to manage the data structures that can map an object across to the correct serializer to use to be able to transition that object into a binary form, and vice versa. So when given the binary, it can determine what the type ID is and what serializer should be used to deserialize that binary. Okay, so let's have a look at the POF Serializer Mechanism. So here we can see that our atom remains unpolluted of serialization framework and has no compile time dependency on the serialization framework. And we can see that we have this atom POF serializer, and the serialize and deserialize should look very familiar to what we had in the read external, write external. And we can see that we have this XML snippet as well. And in this XML snippet, the serializer is explicit because from the atom we can't infer the serializer to use. And let's take a quick look at the annotation approach. So here we can see that we have the atom class, it's marked as being portable, and also it has these various portable properties. And we can see that we also have this XML snippet, which is identical to the first use case. Right? So from the atom, we can infer the serializer to be used by the fact that atom itself is annotated with the portable annotation. And one of the issues with this approach, so this was introduced in 3.7.1, and one of the issues that we found with this, and from feedback from customers they also agreed with us on, is that the developer, as well as providing the class file with the portable annotation present, must also provide a POF configuration file. The POF configuration file will register the type with the POF context. This seems unnatural to the use of annotations, as annotations themselves are points of configuration. So to alleviate these concerns, in Coherence 12.1.2 we've introduced a new feature called the POF Configuration Generator. The basic principle is to generate the POF configuration file based on discovered class files that are annotated with the portable annotation. The discovered class files will be based on a given set of resources. This given set of resources could be considered collectively as a class path. So it's a number of resources where each resource either links to a jar file or the root of a class's directory. The one piece of information we don't have during the generation process is a type ID. So the annotation itself doesn't mandate a type ID, and so we must allocate type IDs as we discover types. Now this allocation is predictable based on the same number of class files that are discovered during a generation. Also, the generator can accept a previous POF configuration file. This allows previous generations to be respected and not have collisions or replace types that were generated previously. Also, we support the idea of a Gar file. The Gar file is a new concept introduced in Coherence 12.1.2, and it stands for Grid Archive. It can be considered very similar to a WAR file. The Gar file itself has a structure which includes a lib directory which can have many jars within that lib directory, and also it can contain many coherence configuration files and must provide a descriptor file, a coherence application XML file. The generator understands the structure of a Gar file and can scan the Gar file to determine all class files annotated with the portable annotation. In addition, the POF configuration file that's generated will be inserted into a new Gar file with all the previous contents. The descriptor of the Gar file will also be updated to reference the new POF configuration file. The POF configuration generator can either be invoked command line or through a consumable API. Out of the box with Coherence 12.1.2, we ship with shell script and a batch script. Both scripts accept a number of arguments, with one being mandatory and a number of optional arguments, but we'll go through those in the demo. In addition, we decided to make the generator consumable via an API. The reason for this is that we understand that there are many contexts that the generator may be used under, and thus we wanted to be amiable to work under these contexts and to interoperate. So the API is relatively simple to use. It uses a builder style, and we'll go through that shortly. What this means is that we can integrate with the various contexts that may be present. So we see a number of ways that the generator itself can be used. The first being the one-off use case, where you want to generate a POF configuration file based on a number of class files, and then have that generated configuration file either deployed with or embedded into the application when it's deployed. The other option we see is to hook the generator as a part of the build lifecycle. So during something similar to a Maven packaging phase, you may want to suggest that the configuration is generated and then embedded into the application artifact. The other use case we see potentially is through runtime use. So when it's required and a configuration file isn't present, we could then generate the configuration file that should be used. And we'll go through that last use case in a bit more detail and show you an example of how you could do that. In addition, we don't load the classes via the JVM or the class loader that we are given or construct. Instead, we use our own embedded disassembler to read the class file as a stream and determine what annotations are present. So this means that we have no dependencies on any third-party disassemblers, but more importantly, we don't cause the JVM to hold references to that class file. So this means that as soon as the generation phase is completed, all the objects that we created as a result of that generation phase are reference-free and can be collected. So let's have a look at a bit of a demo. Let's open up a shell. So we'll remove this PowerPoint presentation and get to a shell window. And let's have a look to see what we have here. So we have a coherence directory with a bin, which contains the shell scripts and batch files. And we have the coherence directory with a lib directory, which contains the coherence jar. This is a light version of the distribution. It contains only the things I need. So we also have a POF directory and a POF Gar directory. So let's pop into the POF directory. And here we can see that we have the app objects jar. Let's interrogate this jar. We can see that we have the classes that we've mentioned previously in the slides. And so each of these classes are annotated with the portable annotation, and thus should be amiable to the generator. And we should see user types generated by running it through the generator. So let's execute the generator. So the other thing that might be worth noting here is that the coherence bin directory is a part of my path, so I can execute the contents of that. So let's execute it without any arguments. And if we scroll up a little bit here, what we can see is that after some version information and descriptions, we can see that we received an error because the root is a mandatory argument. So we failed to specify a mandatory argument. And let's have a look at some of these arguments. So root is mandatory, and it is a path separator, separated string of directories or jar files. And it's what we referred to previously as the class path, which is input for the generator. It can also be a Gar file, and if it is a Gar file, then the output will also be a Gar file. Okay, and then we have some optional arguments. So first of all, we can specify out, which specifies what the name of the output file should be. So when under the guise of a Gar file, that is the name of the output for the Gar file. When not using a Gar file, the output is the POF configuration XML file. The config directory specifies a previous POF configuration file to ensure that those user types are honored and no conflicts are created in the new POF configuration file. The include refers whether we should inline the previous POF configuration file into the new file, or whether we should include a reference to it. Packages is a comma-separated list of packages to narrow the remit of the class file scanner. Start type ID is the type ID to start allocating type IDs from. Okay, so let's execute this against our jar file. So this will go off and execute, and it will hopefully find the 5 classes that are within the app objects jar and generate a POF configuration file from them. And so let's have a look at the contents of that configuration file. So we can see that we've found all 5 of our classes, and as well as that, we've generated type IDs for them. So one thing I'm going to do is edit this file. So let's just remove all other type IDs and change the atom so that it has a type ID of 1002, and this is effectively stimulating a potential collision, and that's what we're trying to avoid. Okay, and we'll just kill this buffer, and if we look in here, we have my previous POF config XML and the POF config XML, which was the generated one. So let's just specify the previous POF configuration file. I'm also going to leave the POF config XML that was previously generated there. And then this is going to go off and scan, and what we hope is that the atom will remain with the type ID of 1002, and all other allocations will be made around those already allocated type IDs. Okay. And the other thing to note here is that we found that the file POF config XML already existed, and so we generated a file with a unique suffix, which in this case was -1. And let's have a look at the -1 XML file. So here we can see that we have electron, neutron at 1000, 1001. We've respected the previously reserved atom at 1002, and then we have 1003, 1004 as expected. Okay, let's just kill this buffer, and let's now stress all the other arguments. So we can decide whether we wanted to include the arguments. So let's just have a look at all the other arguments we can specify. So we can include packages and start type ID. So let's include, which will mean that we will have a reference to my previous POF config XML, and the atom should not be present in the generated POF configuration file. And also let's specify the start type ID as something other than 1000. So this will go off and generate, and we should have a POF config -2.xml. So let's have a look at this file, and we can see that we have an include of my previous POF config, which contains the atom. The atom isn't specified here, and we have our electron, neutron, nucleus, and proton. So let's remove that. Let's pop into the Gar directory. So the Gar within the Gar directory, we have a grid archive.gar. And if we have a look at the contents of the grid archive Gar, we can see that we have a Coherence application XML file, which is a descriptor, and we have the same classes with the same annotation. So first of all, let's extract from the grid archive the Coherence application .xml file. And let's take a look at it. So we can see here that the Coherence application XML file is pretty much empty. Okay. So let's just remove it and remove the meta directory. Let's execute the POF configuration generator and pass in the root as the grid archive. And let's see what gets output. So in this case, we'll actually see a new grid archive created with the contents of the previous grid archive and hopefully with a generated POF configuration file. So let's take a look at the contents of it, and we can see that we have the Coherence application XML, the POF config, and the classes. So let's verify the contents of the meta directory. Okay. So first of all, the Coherence application XML file should have a reference to the POF configuration file, and you can see here that that's exactly what we've got. So that's great. So let's remove that, and now let's just have a look at the POF config, and let's just verify that it's as we expect, and that looks great. So let's just remove this, and obviously all the other arguments that we mentioned previously will work under the Gar also. So there's one other area that I mentioned previously that I wanted to show now, and that was programmatical use of the generator. So let's bring up our IDE and show an example. So let's first of all focus on the generator and how it can be used. I will explain where this generator is being used shortly, but let's first of all concentrate on the API. So we have this thing called a POF config generator. It accepts a number of dependencies, and in these dependencies I can set various things. Okay, so here we can see that I can specify the output path, the packages, the POF config, the include, the path route, and the start type ID. And these should look very familiar to you because they're the same as the arguments that we can specify through the command line. So the POF config generator can be used programmatically using the exact same arguments that we specify via the command line. So in terms of its actual use, all we need to do is create a new instance of the generator, provide it our dependencies, and then call generate. And at the result of generation will be a file with the new POF configuration file. So let's explain a little bit about the usage here. So this is a generated POF context. Generated POF context extends the configurable POF context. And I'm sure you would recognize the configurable POF context. So let's have a look at our cache configuration file. So this is the cache configuration file we use. And here we can see that we specify the serializer. And we specify an instance of the generated POF context. And in this use case, we specify a package. Okay, so this is actually a comma-separated list of packages. And if we look back at the generated POF context, it accepts the package names, a comma-separated list of package names, and also it accepts a POF configuration URI. So that could be a previous POF configuration where we have the type IDs that we want to respect. Under this use, what we're doing is we're generating the POF configuration file at runtime and on demand. So opposed to having it as a part of the build process, we actually generate the POF configuration file for every member. So as soon as we start the service and we require the serializer and we instantiate the serializer, at that point we will generate the POF configuration file and use that POF configuration file. and that's where this is done. And all this is really highlighting is the API under this particular use. The generated POF context is something that we will more than likely put into the incubator soon, and you'd be able to download it and reference it from there. Additionally, we have a test which validates, so it uses the generated POF context, and it validates that we can serialize a helium atom. We can teleport it via the serialization framework, and then receive a different atom and assert that it has the same number of electrons, neutrons, and protons as the previous atom. And if I execute this test, we can see it goes off and executes, and all the assertions are successful. In addition, we can actually see the POF configuration file that's output. And again, this should look very similar to what we saw through the command line invocations. Thanks for listening to this screencast on the POF Configuration Generator.